Now, what we're going to be interested in, we're interested in the most probable distribution of energy between things like the ice cube and the coffee, or the table and the marker. And so we're interested in probable distributions of energy. So what we're going to do is we're going to look at this at the microscopic level first and think about ways of distributing energy in small systems. So let's think about our model of one atom. So here's our one atom that we have one atom is 3 oscillators. So here's the first one. And here's the second one. Here's the third one. They correspond to X, Y, and Z oscillations. So this is one atom. And suppose that we have 2 quanta of energy that we could put into this oscillator to make it oscillate more, and put into this atom. Well, it could go into oscillations in the x direction, or it could go into oscillations in the y direction, or it could go in the z direction. We just played with that a little. So let's say we put it into, so we have 2 quanta of energy to put in. So one possible thing we could do is put it in this one. And so if we write down the number of quanta of energy that are in this particular oscillator above the ground state, we can never be below the ground state. We would say that this corresponds to putting 2 quanta there and 0 there and 0 there. Okay? Or, of course, we could put it there instead, and that would be 0, 2, 0. Or we could put it here, and that would be 0, 0, 2. So there are 3 different ways to arrange 2 quanta of energy among 3 oscillators, right? Not right. So what else is there? You can put only one. Okay, so let's not do the drawings, but so we could do 1, 1, 0, or 1, 0, 1, or 0, 0, 1. What? Oh, right, we are. Sorry. So it would be, what's the one I didn't do? This one, right. That one. Yep. Is that it? Okay, so it looks, I don't see any other ways to arrange it. So it looks like we have counted 6 ways to arrange 2 quanta of energy among 3 oscillators, or 1 atom. So we're basically just learning to count here. So 6 ways. 2, 0, 0, 0, 2, 0, 0, 0, 2. Okay? So let's see if we can apply that to another system. Suppose that we had 4 quanta of energy to arrange in 1 atom, so 3 oscillators, 4 quanta. So the question is, how many different ways could we find to arrange 4 quanta of energy among 3 oscillators. And we suggest that you do it by just writing down the possibilities, counting on your toes. So yes, we're going to have an equation for it, but right now we haven't got it yet. So we're just counting because we need to make sure that the equation actually works. Well, you got some different things. Half the class got 3 and 30% got 4. So 3 times 4 is 12, right? And that's why you said 3. You didn't count. So let's count. So we can do 400 or 040 or 004. That's all the ways we can do all 4 quanta in one, right? So that's 3 ways. And then we need 3 and 1, don't we? So we can have 310, 301, 031, 130, 013, 103. That pretty much does that. So that's 6 of those. Are we done? We're not done. 2s. So 220, 202022. We done? So 3 of those. Oh, 2s and 1s. Okay, so we have 211, 121, and 112. There seem to be 3 of those. So we have 6 and 9, looks like 15 ways. So it's not as simple as number of oscillators times number of quanta, is it? Because 15 doesn't look like some easy combination of 4 and 3. So what we end up with is a combinatoric formula, which some of you may know. And I'm not actually going to go through the derivation of why it applies to this situation, but it is explained in the book in a really easy way to follow. So I'd suggest reading that. And it turns out that the number of ways, we call it capital omega. I'm not sure why. So the number of ways of arranging some number of quanta, q quanta, among n oscillators. And that's equal to, let me write it up here where you can see it. It's a q plus n minus 1 factorial divided by q factorial times n minus 1 factorial. So let's make sure it gives us the right answer for the thing we just did. We got 15. So let's make sure this comes out to 15, actually. Let's see how we do this. So here we had, so what would Q be in this case? 4. So Q is 4, and the N is 3. So we'd get 4 plus 3 minus 1 factorial divided by 4 factorial times 3 minus 1 factorial. So 4 plus 3 is 7 minus 1 is 6, so that's 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1 times 2 times 1. And there's some cancellations here that happen, so we can, those two things cancel, and so we're left with 30 on top divided by 2 on the bottom, so that does indeed come out to 15. Now we're actually going to be interested, so do you have questions about that? No. We're going to be interested in doing these calculations for lots more than one atom, lots more than 3 oscillators, lots more than 4 quanta. So we need to learn how to do this on our calculators in an easy way. And of course you could just take this, use the factorial key on your calculator and do this and this, but the problem is that when the numbers get big, you start getting overflows. And so this equation, this formula, is actually available in your calculator. Okay, it's called the Combin formula. Combin is the number of the, and here's how it works. So let me blow this up so you can see it. So first of all, you've got to get your calculator into scientific notation because these numbers get big. So if you have an 83 or an 83 plus or something, first you need to put your calculator in scientific notation. So you use mode and then highlight psi and then enter. And the function in Excel and VPython and other computer tools is called Combin, and it's defined this way. So get your calculator into scientific notation first. And here's what Combin does. If it's defined with two numbers a and b, and that's equal to a factorial over b factorial times a minus b factorial. And so if you think about it, we want q plus n minus 1 factorial. So a is q plus n minus 1, and b is q. So what we want is the combinations of q plus n minus 1 and q. That's what we want to tell the calculator or VPython or whatever it is we're using to calculate. So how do you do this? Well, on a TI-83, you press the math key, and then you scroll across. There are 4 things at the top. You scroll across to probability, and you choose 3, which gives you this n choose r. And the way the syntax works on the 83 is that, and its relatives, is that you would end up entering 5, and then doing that operation, and then entering 2 if you wanted to do 5 and 2. On the 89, it is a little bit different. You press math and choose probability and choose NCR, but on the 89, it's actually a function, so it's NCR 5, 2. Okay, so let's try one and just see if we can calculate it, because we want to have some bigger things. Well, let's do this one first. It's easy, but then we'll do a big one, and you'll see why you need this. Four oscillators, which is 1 1/3 atoms. We're not being physical. We're just doing a calculation. 2 quanta. What calculation would you do? This is worth figuring out how to do because it's just we're going to do it a lot. So, okay, you got answer 3, which is 10. So what we calculated was we had Q was 2, N was 4, so we had the number of ways would be 2 plus 4 minus 1 factorial over Q? We have 2 factorial, 4 minus 1 factorial. So that came out to 5 factorial. And what you typed in, presumably, was 2 plus 4 minus 1, NCR 2, or some variant of that, right? Well, because the definition says that the way the combin function works is what you're feeding to it. The first number is Q plus N minus 1, and the second number is Q. So here we've got Q plus N minus 1 and Q, whereas this is $10. So most people got 10. You get 10? Okay, let's work it out. This is one that's small enough that we can work out ourselves, so let's work it out. We've got, it's going to end up being 5 factorial divided by 2 factorial times 3 factorial. So that is going to give us 5 times 4 times 3 times 2 times 1 divided by 2 times 1, 3 times 2 times 1. Those cancel. We've got 20 divided by 2, which looks like 10. Yep, 2 plus 4 minus 1 here. You might need to use parentheses, or I mean, you can also add it yourself. And then 2 here. So everybody get that? All right, let's try a big one just to see, because we're interested in lots of atoms and lots of oscillators. So if we have 100 oscillators and 300 quanta of energy, what are we going to get? And 2 is correct. All right, so you need to be able to do this. If you're having problems with this, talk to me or a neighbor after class and get it straightened out, because we need to be able to do this.